So we will start this session. This is embedded systems and real-time optimization. So the first speaker is Yixiao Xing. He will talk about multi-core benchmark framework for real-time embedded systems. So we will leave the floor to him. Feel free to start.
Thank you very much. Thank you very much. I'm Yixiao from Nagoya University and Takada Laboratory. It's my honor to be here to introduce my research with you. And my topic today is RTESbench, a multi-core benchmark framework for real-time embedded systems. And my introduction will be divided into 6 parts. And at the first part, I will introduce you the background of my research. And I will explain you why we think that the multi-core system benchmarking is so important and the challenges when we evaluating them. As we all know, embedded systems with multiple cores have been rapidly introduced to meet the growing performance demands. And in order to understand the behavior of the systems and to evaluate them, performance evaluation methods and tools are very important for ensuring the real-time behavior of the systems. And as long as we know, for single-core systems, there are both well-researched statistical analysis method and benchmarking methods, and they are developed very well. And unfortunately, for the multi-core systems, evaluation methodology are seldom discussed, especially these features that only multi-core systems have. For example, the inter-core interface and any other resource contention may influence the system badly. And the challenge when evaluating this system is that we should perform evaluation methodology for multi-core system evaluating. And by using this methodology, we should establish the scalability of different RTOS across various hardware platforms. And we need a convenient research and develop tool. So we want to develop not only a methodology to evaluate such systems, but also we want a tool to simplify the work. And here comes to our goals and contributions. Our goal is to design and implement a benchmark framework. Such framework should allow the implementation and continuous update of various benchmarking scenarios. And it also should support a wide range of hardware platform and RTOSs. And it should automatically evaluate a specific target based on user-defined requirements. And so our contribution is design and finish such a proposed benchmark framework. And we implemented a prototype on 3 different systems applying our multi-core benchmark methodology. And through the experiment, we revealed the system performance characteristics, which we defined as the system behavior change under different contention. And we also found some features and bottlenecks through evaluation results. I will introduce this part in the later part. And then I will introduce you the framework design of our framework from 3 perspectives. The first perspective is the module perspective. Our benchmark have 5 modules. The first module is the benchmark scenario module. In this module, we contain scenarios templates that are written in our general interface. And with such interface, we can write the benchmark without any concern about the detail of hardware and RTOS. It's very convenient. And in the RTOS and hardware details module, it contains some hardware information and RTOS information. If you offer some implementation to the interface we offered, you can add new support to the RTOS and hardware without any further work. And also, some compile and execution script should be stored here too. And the third part is the user parameter module. And in this module, benchmark user can offer parameter to decide the target system they want to evaluate, and other parameter like the number of active cores or some test duration or stress step. This parameter can help the generator to generate the C source code automatically. And the fourth part is the executable code generation part. Executable code generator is written in Python and take charge of the generation of executable C source code, and then the C source code can be executed and evaluated automatically. And the final part is the analysis part. In this part, the output of the benchmark can be captured and be outputted with histogram or line chart. And then I will introduce you the user perspective. Three kinds of users can use our framework to do some job. For example, benchmark user. As a benchmark user, for example, like researchers of benchmark or some engineer who want to select suitable hardware or RTOS. They want to evaluate the system to see whether they fit their application. Then they can use our benchmark to see the performance and the different stress contention and can figure out the feature and the bottleneck of the system. And as a benchmark developer, they always need to test their new developed benchmark scenarios. And then they need a platform to test their benchmark methodologies. Thus, they can use our framework to finish this job rapidly. And then the third user is the system developer. They also can offer some information to the framework and rapidly evaluate new devices or RTOSs. This is the three user perspective. And finally, I will introduce you the simple workflow of our benchmark framework. Please pay attention to the red arrows here. And first, the user decide the target system and the other features like the core number or stress step as input parameter. And then the executable code generator locate the platform templates in the scenario module or the detail module, and then generated the C source code with the information offered. And the C source code is then placed to the project routing and executed by a script offered in the RTOS and hardware detail module. Finally, the serial output is captured by the analysis module, and the data is outputted and in the histogram or line chart form. This is the workflow of our benchmark framework. And then we implement the methodology and the framework design into a prototype. The key point of the prototype is mainly two parts. First, the benchmark scenarios we select, and the next one is the target system we selected. And the key benchmark scenario we used in our prototype is just based on our former work in the article below. The main idea is that in order to understand the behavior of multi-core systems, it is essential to evaluate their performance under different contention scenarios, which we think is very, very important in multi-core situations. We treat the RTOS and the hardware as an entirety and test them on API levels. We first group the API by resource access path, just like shown in the left hand. And the access path based on the fact that we can group them on the fact that state-of-art RTOS shared similar API design, so we can group it and targeting them. In this prototype, we target on most commonly used API and group them into 6 patterns. The patterns are shown on the right picture, and we have 6 patterns and selected their typical API. For example, API that get the object information or acquire some semaphones. They are typical API and it can be tested in our framework. And then we designed a workload evaluation and scalability evaluation. The workload evaluation part is from the idea of stress workload evaluation. We place the target API on one core while stress are placed on the other cores. We adjust the frequency of the stress workload APIs to reproduce potential contention scenarios. And the stress is designed within 2 dimensions, just like the picture on the left. The first is the access target. It is because the difference between task and object accessing can influence the behavior badly, especially in finer grained system. And the shared resource access and the private resource access is the other feature we we designed. It's also important because shared resource access may cause badly delay in the overall system. We adjust the ratio of the access to reproduce the contention. This is the workload evaluation part. And to the scalability part, it is just similar. We want to figure out how the overall performance changes while the active cost is increasing from 0 to the maximum. So we add the active core one by one and see how the overall performance changes to do such scalability evaluations. And then is the system detail part. In this part, we selected 3 different systems which contain some representative RTOS and hardwares. For example, in the first system, we selected the NATIX, which is a POSIX-style RTOS. It is very representative because if we can do some work on this RTOS, and then we can use the methodology to different RTOS, such as Linux or other POSIX-like RTOS. And we select the Sony Presence board. It's a 6-core board, and the system 2 is the FreeRTOS and the X-core AI. The FreeRTOS is the most widely used open source RTOS in the world, and the X-core AI have 16 logical cores on 2 physical cores. It is very suitable for our evaluation. And to the system 3, we select the Topaz FMP, which is developed in our laboratory, and it is a special RTOS with fine-grained lock design, which we can see how fine-grained lock design can work in multi-core situations. And we select the Xilinx board with 4 ARM cores in this evaluation. And then I will introduce you some results and interesting point in our experiment. At first, we want to figure out the baseline execution time of the 3 different systems in 6 different patterns. We want to see the performance characteristics, which in other words, the change of the performance of the API under different stress. So we want to see the baseline execution time, and after that, we want to normalize the data with the baseline execution time. So we first figure it out and then do other evaluations. In the benchmark storage workload evaluation, with the stress workload evaluation, we can see the overall performance change under different stress while also find some features and bottlenecks of the RTOS and the hardware devices. The picture on the left shows the overall performance with the parallel stress workload. And the picture on the right just figures the FMP situation when the resource access is contentional. Let me raise some examples of the interesting point in our experiment. Please see the green line here. It shows the benefit of fine-grained lock design in multi-core situations. It works very well when the resource access is parallelized. And another interesting point is that we can see the orange line. It represents the behavior of FreeRTOS on X-core AI. We can see the behavior do not change after we increase the cores from 7 to 14. This is just because the design of the hardware is based on 2 physical cores, and the cores do not interfere each other. This fact shows that our benchmark framework and our methodology can have the capability to understand some feature and the bottleneck in the design of hardware and RTOS. That's why we think our framework can work well. And this picture shows the benefit and the special point of the fine-grained lock design. We can see in the normal part, we can see in the right picture, in the normal part, the fine-grained lock works very well. And when the storage reaches the maximum, we can see the performance may be worse than the giant lock design. So how to control the balance between the giant lock design and the fine grained lock design should also be a very interesting topic. And we can find such interesting topic just using our benchmark framework. And this is another interesting point of our benchmark frameworks. And so as the scalability evaluation, we can also see the overall performance behavior of the multi-core systems. And also we can see some interesting features of the hardware and RTOS. For example, on the right hand, the picture shows that when the active core is increasing, the behavior of the Natix RTOS is very strange. Some cores do not work when 6 cores are activated. This is just because maybe memory is limited. And such figure shows the problem in the design of the RTOS or the devices. And then I will give you the conclusion and the future work of my work. And we designed a flexible benchmark framework for embedded systems and optimized and implemented our former multi-core benchmark methodology and built and evaluated the prototype on 3 different systems and obtained the performance characteristics and some feature and bottleneck of our systems. In the future work, we want to expand our method to more representative RTOS and hardware platforms and integrate modules such as performance monitor unit in ARM to enable deeper analysis of our performance data. And we also want to optimize our benchmark scenarios by concerning real-world task feature, which is my next topic. And that's all of my speak. And thank you very much for your attention.
Thank you very much. Any questions for Xiaoying? Any questions or comments? So yeah, I have one, which is pretty much high level. So you mentioned in the paper you have 3 system prototypes to evaluate your benchmarking frameworks.
Oh, yes.
So why you chose these 3 systems? Any particular reasons?
Yes. One reason is we want as many core as possible. So we chose some multi-core devices. For example, Sony's Presence have 6 cores and X-Core AI have 16 cores. And the other reason is we want to test as much type of RTOS as possible. For example, Natix is a POSIX style RTOS, and on the other hand, the Topaz FMP is Japan-made RTOS with fine-grained lock design, which are seldom seen in the state-of-art RTOS. So by testing them, we can see some difference between the devices and the RTOS systems. And from this, we can see some idea when we further design or develop the RTOS or devices.
Okay. Yeah, thanks. I think in the interest of time, so we move to the next speaker. Thank you.